Hi everyone, let's talk about the squaring function with domain R. The rule given by f of x equals x squared, domain is all reals. This is a good example of an even function. We'll talk about symmetry here later on. Well, if you don't know how to graph y equals x squared, do some point plotting. The domain is all reals, so let's plug in various real values for x, probably integers, right? The square of 0 is 0, so the origin, 0, 0 is on the graph, over here. Over here, the square of 3 is 9, so the point 3, 9 appears on the graph. That's over here. But also, the square of negative 3 is also 9. So the point negative 3, 9 also appears on this graph over here. And we see this kind of symmetry. If the point, I'll do this in green. If the point x comma y lies on this graph, then that means that the point opposite of x comma y will also lie on this graph. So the graph of this function, which is an even function, will exhibit this symmetry about the y-axis. The graph of y equals x squared is symmetric about the y-axis. That's true of the graph of any even function, such as this one. Something else you should know about the x squared function, remember that squares of real numbers are never negative, which means that the outputs are never negative. The y-coordinates are never negative. So the graph never falls below the x-axis. Again, every point x, y in the graph has a mirror image partner about the y-axis, opposite of x, comma y. This demonstrates the symmetry about the y-axis. But let's prove that algebraically. Why is this squaring function an even function with that kind of symmetry? A function f is even if and only if, and remember, this is going to describe symmetry about the y-axis, where y is a function of x. We're going to assume throughout this section that y is a function of x. A function f is even if and only if, well, when does this happen? If f of opposite x equals f of x for all x in the domain of f. So in other words, anytime you have an x-coordinate where we have a point on the graph, here the domain is all real numbers. So we have points with all real numbers as x-coordinates, all right? But every time you have an x-coordinate in the domain, you're going to get a point on that graph. And then at the opposite value of x, you're going to get another point with the same y-coordinate. Okay, for all x in the domain of f, okay, at opposite x, you get another point with the same y-coordinate. Again, for all x in the domain of f, you get a point with a y-coordinate, and also at his partner, opposite of x, you get the same y-coordinate. So for example, at x equals 3, we got a function value that was positive 9. But at x equals negative 3, we got that same function value, or y-coordinate, of positive 9. Opposite x-coordinates in the domain yield the same y-coordinate. And by the way, in order for these pairs of opposites to exist, we do need the following to be true. The domain of f must be symmetric about 0. That's to ensure that for every x-coordinate in the domain, its opposite will also be in the domain. So in order to have an even function, the domain must be symmetric about 0. This statement kind of assumes that property. So let's quickly go over the proof for this. I wouldn't expect you to do this now, but later on in section 1.7, maybe. Let's prove algebraically that the squaring function on R is an even function. Again, we're assuming the domain is all reals. If the domain is not all reals, then we may not have symmetry. This here would not represent an even function if you restrict the domain. For all x in the reals, the domain of f, okay, here's the idea. You're going to ask, what's the deal with f of opposite x? So when you see something like f of opposite of x, the key word here is substitution. What happens when you substitute opposite of x or negative x? A lot of us say negative x. What happens when you plug in opposite of x or negative x into x over here? You get the square of opposite of x. See, over here, f takes x and squares it. That's the basic rule. What does f do to the opposite of x? Well, again, it squares the input, the argument, the opposite of x. But the square of opposite of x takes us back to x squared, the same expression we got over here. Or its equivalent. Of course, x squared is equivalent to itself. So notice that the function values at the opposite of x and x will be the same. We get x squared in either case. F of opposite of x is equal to f of x for all x in the reals, the domain, which means that by this definition, the function is even. The function is even. This is the official way to end a proof, QED. It's Latin for this. I won't pronounce it. That often denotes the end of a proof. Some people will use 3 dots like this. Fans of the band Rush will appreciate that. Okay, or some books use a solid box. Okay, but QED is the nice Latin you can use. Once again, why is this squaring function even? If we replace x with its opposite as the input, we get equivalent outputs. We get x squared, that is f of x in both cases. For example, 3 and negative 3, x and the opposite of x give us the same function values, the same y coordinates. F of opposite of x over here, the y coordinate here, is equal to f of x over here, the y coordinate here. These are equal. Okay, busy picture. Okay, so why do we call these even functions? What are some other function rules that'll get us even functions, where the domain is all reals? We have f of x equals x the second, and what else? Including some guys we saw before.